Welcome to this explainer. Today we're zooming way in to look at the absolute foundation of the physical world. We're going to figure out how literally everything you see, touch, and interact with is actually held together. Spoiler alert, it is not by tiny physical hooks or, microscopic superglue. Nope. Instead, our entire universe is bound by these completely invisible forces and some pretty intense atomic negotiations. Let's dive in. To really get a grip on this, let's start with a mystery. Why does a diamond, which remember is just carbon, why does it so easily scratch glass, while a copper wire just bends effortlessly right in your hands without snapping? I mean, they're both just collections of atoms, right? So what exactly makes these materials behave in such wildly different ways? Well, the answer lies entirely in how those atoms choose to interact with their neighbors. But first, we actually need to shatter an assumption a lot of us probably picked up in high school chemistry. You know those plastic model kits? The ones with the little colored balls connected by those gray plastic sticks? Yeah, those are great for visualizing things, but real bonds aren't physical sticks. They're invisible electrostatic forces. It's so much better to think of atoms not as objects bolted together, but as tiny entities constantly negotiating over their most prized possessions, their electrons. And don't worry, we're not going to focus on any complicated numerical formulas today. Instead, we are just going to build a real intuitive feel for how these microscopic negotiations actually work. Okay, so to understand why that copper wire bends so easily, I want you to imagine a commune where absolutely everyone freely shares everything they have. There's zero private property, just this massive shared pool of resources. As it turns out, this is exactly how metals behave down at the atomic level. This communal sharing is what we call metallic bonding. In a metal, like copper or iron, the atoms actually release their outermost electrons, the valence electrons. They literally just let them go. And by doing this, the metal atoms become positive ions, and all those released electrons, they pool together to form this massive shared sea of what we call delocalized electrons. So picture that positive ion core just sitting there, happily embedded within this invisible, negatively charged electron sea. The entire structure of a piece of solid metal is held together purely by the electrostatic attraction between those positively charged cores and the negatively charged seas swarming all around them. Now, because these electrons are delocalized, meaning they aren't tied down to any one specific atom, this bond is completely non-directional. The electrons are shared equally everywhere, just flowing freely through the material. And actually, this free-flowing sea is the exact reason why metals conduct electricity and heat so incredibly well. And because the bond is non-directional, an atom isn't rigidly locked into some specific angle with its neighbor. Entire planes of atoms can just effortlessly slide past one another without breaking the overall bonds, all because that electron sea simply shifts and adapts right around them. This dynamic movement is the intuitive reason why metals are malleable and ductile. It is literally why you can bend that copper wire into a loop without it just shattering in your hands. All right, let's completely switch gears here. Contrast that free-flowing communal sea with a highly restrictive, super exclusive partnership. Imagine a scenario where very specific partners agree to share a precise number of resources and they absolutely refuse to share with anyone else. No free-for-all here. This is covalent bonding. It is a phenomenally strong connection that's super prevalent in non-metals. And honestly, it's the foundation of the organic compounds that make up our bodies, our food, and life itself. Instead of just tossing electrons into a giant communal pool, two atoms specifically share one or more pairs of valence electrons right between themselves to fulfill a definite, rigid valency requirement. The crucial difference to grasp here is the physical effect this has. Metallic bonds, they're non-directional and flexible. Covalent bonds, on the other hand, are highly directional and incredibly rigid. Because the electrons in a covalent bond are shared locally between very specific atoms, they lock those atoms into exact geometric shapes. They definitely cannot just gracefully slide past each other like our metal atoms did. And this directional rigidity brings us right back to our very first question. A diamond is incredibly hard precisely because every single carbon atom within it is locked into these strong, specific tetrahedral covalent bonds with 4 other carbon atoms. There's no sliding, there's no yielding. To bend a diamond, you would have to literally snap these massive rigid chemical bonds, which obviously takes a tremendous amount of energy. So we've looked at free-for-all sharing and we've looked at strict partnership sharing. But what happens when atoms engage in a completely unequal, totally aggressive trade? Like what happens when one atom is just a total taker and the other is a complete giver? Well, that creates an ionic bond. This happens when an atom that really wants an electron, one with a high electronegativity, completely steals an electron from an atom that's perfectly happy to give it up. A classic everyday example is sodium donating its electron to chlorine. The sodium becomes a positive ion, the chlorine becomes a negative ion, and bam, they snap together purely due to the massive electrostatic attraction between those opposite charges, giving us NaCl, or common table salt. This completely unequal trade creates these rigid, alternating grids of positive and negative charges. Now, they are very hard, but unlike our flexible metal, they are ridiculously brittle. Think about it. If you hit a block of salt and force a layer of atoms to shift even slightly, suddenly positive ions align directly with other positive ions. They violently repel each other, and the whole crystal just shatters. Oh, and solid salt doesn't conduct electricity because the electrons are locked up so tightly. But if you dissolve it in water, the ions break apart, float freely, and suddenly you've got a highly conductive solution. Okay, finally, moving beyond the communal sharing of metals, the strict sharing of covalent bonds, and the outright stealing of ionic bonds, there's a fourth force. It's a much weaker, incredibly subtle force that is just constantly working in the background of everything around us. It's kind of like a fleeting static clang. These are called van der Waals forces, or sometimes secondary bonds. They pop up from electrostatic interactions between electric dipoles. And what's really fascinating here is that these forces are present in absolutely all materials, no exceptions. However, because they are relatively weak, they usually only become the dominant glue, dictating how a material behaves when those stronger covalent, ionic, or metallic bonds are completely absent. To really grasp van der Waals forces, we have to embrace a little bit of physical uncertainty. You see, electron clouds are not perfectly static, frozen spheres around an atom. They're actually constantly shifting, sloshing around, and fluctuating in completely unpredictable ways. At any random nanosecond, there might just happen to be more electrons on the left side of an atom than the right. That creates a temporary dipole, like a tiny momentary magnet that briefly tugs on the atoms right next door. Now, these fleeting forces come in a few different varieties, depending on whether the dipoles are permanent or just momentarily induced. But there is one special standout we have to mention: hydrogen bonding. When hydrogen bonds with highly electronegative atoms like oxygen, it creates a very strong, permanent dipole. This uniquely powerful van der Waals interaction is the exact reason why water is a liquid at room temperature instead of just floating away as a gas. Pretty wild, right? So now that we've built a solid intuition for how atoms negotiate, whether they share freely, share strictly, steal, or just exert that subtle static pull, let's zoom back out. Let's look at the big picture of how these invisible bonds literally shape our macroscopic world. Again, without worrying about any of the underlying mathematical formulas or numerical cohesive energies, we can see exactly how the very nature of a bond dictates reality. The strict sharing of covalent bonds gives us the unyielding rigidity of a diamond. The non-directional, free-flowing electron sea of metallic bonds gives us the flexible, conductive copper wire. The mechanics happening all the way down at the microscopic scale directly dictate how things behave up here at the human scale. As we wrap up this explainer, I want to leave you with a bit of a challenge. Next time you interact with perfectly everyday objects, when you bend a paperclip, when you sprinkle salt on your dinner, or even just hold a glass of cold water, take a second to look past the surface. Try to visualize those invisible electron seas, the rigid atomic partnerships, and the subtle electrostatic pulls that are silently holding your entire physical world together. Thanks so much for joining me, and never stop questioning how the universe works.